right? This page is the same thing, and they were able to finish their training and get a loss of 1.307 when they ran the actual test to see how well it was doing versus the ground truth. Uh, they were able to get 56% accuracy. And this is something that's very common. If you're getting something lower than that, then you definitely made your model worse. And maybe this is where you need to think about changing some things around. This is also per class accuracy. So this is you can wire up a way to get your per class accuracy. I'm not going to get into how you enable it for data parallelism and GPU and things like that, but because I just wanted to give you a quick overview of PyTorch models, right? Another big area. So it's like, okay, well that's good, and there is already a pre-trained model. So one of the biggest challenges, and this is something that it's very uncommon that anybody will start nowadays with a model from scratch. Like you're building a model, you're starting completely reinitialize everything. What is very more common is using a pre-existing trained model, right? It doesn't matter it doesn't even matter what domain it's from, because you can go down to a certain level where even some level of training pre-trained is better than no training, and we'll talk about some of the challenges. So you don't have enough data. And this is something that is very common even in some of the more established use cases, just not enough data. Oh, wait, you have enough data. Well, it needs to be labeled. That's a whole another level of challenge, right? Okay, you have both of those things. You don't have 100 GPUs to train your model, because if you try to run your model, it will take like years to train, right? And then kind of going along with the hardware, right? Also the training time. So why struggle with these things? Why don't we just start your journey with some transfer learning? So to me, and this is what you will see an example, is kind of two different ways, right? One is to say warm up your model, right? Using a pre-trained model. So instead of starting from zero, you just say, I want to start with some initialized weights from a pre-trained model, right? Another one is just retraining your model on your data set, right? Because obviously either the CFAR10 data set, the ImageNet data set, or many of the other data sets out there that they've trained the model on may not really relate to some medical image type data set that you are working on, or whatever other field that you're working on, right? Retail objects. But there's definitely some visual features that you can get started on, and you can say, I'm just going to remove the last prediction layer, and then I'm going to have my own prediction classes, which is going to be hot dog or not hot dog, and versus they've trained it on all these airplanes and things like that, right? So those are two different ways of doing it, and let's just do a quick look into. And once again, this is also directly from the PyTorch website. More so in David's model, you will see some of these things applied. So as I mentioned, the two major things, right? One is to how do I fine-tune using an existing model? And then the other one is to use it as a feature extractor, which is essentially to just retrain the last layer with your own labels, right? Somebody's already done a lot of the feature extraction work. You are now just slapping on to the last few layers your own personal use case to get the output. So fine-tuning is of course a little bit more complicated, and the biggest thing to remember in fine-tuning is that they're in this case the person who wrote this, they're using this bees and ants data set, we didn't. Yeah, I don't have it downloaded in this one, but let's just, it looks like this. Okay. The thing to remember here is that we are using an existing model. Okay, so when we input, when we do the training, we are going to input it with the existing model. And let's fast forward that to here, right? And that's going to be ResNet 18. ResNet is a very popular image computer vision model that's out there that's already pre-trained. It's included in PyTorch. So you start with that as your base initialization, right? And so once you define that, and so here when we run the trained model, then we are going to say our model is going to be this ResNet, but we are going to remove some. We are going to say we are going to add our own final layer to it with our own features, and then our own loss and things like that, optimization. So we are going to provide our own parameters, and then we are going to run the training. So at least you are not starting from complete zero. That's kind of the fine tuning aspect of it, and I know David has some of these things in his, so I'm not going to do it much of a deep dive. The other aspect was simply taking an existing model and then chopping off the last 1 layer, 2 layers, if it's a classification layer, or several layers, and then saying freeze everything. So what the model will do is that here's my input data set. It will not change anything in those first 5 or whatever the beginning layers until it gets to a point where it's like, okay, now I'm going to start tuning it, or I'm going to start training on your data set and your classification labels, because you are not looking for airplanes and cars and things like that, but you are looking for the logos of the brands, and that's going to be completely different. Your labels are going to be different, and you're going to train it that way. So the way you do that is by setting this requires grad to be true. So by default, I'm sorry. When you create new modules, it's true, and I'm sorry. So yeah, you want to set it to be false for the ones that you don't want to retrain, and then the ones that you want to retrain, then you put it to true. Yes. I think more so than that, what I'll say is where do you start unfreezing the layers, and that's going to be very dependent on where that model was trained. And I'll say this is that some of these newer models, some of the more complicated models, they work very well even in like just some really completely outside of their domain. But if you the convolutional, and the point is that you start from one space and then you're trying to get to lower level features, right? So it's just that where do you stop and say don't change anything in all these layers, but from here on retrain. It's really your mileage may vary type of thing. So you start with, of course, the least amount of layers that you have to change, and see what kind of results you're getting, and then you go from there. Any comments?
I think it's mostly about how much data you have available to train, and if you do not have a lot of data, and if it's something that's close to your domain, you can apply it. For example, we look into that for object detection. And object detection, most of the models, if not all, unless they use existing data sets, and there's no hurt in just retraining the model with some adjustments. But if you have limited resources available, and that's the example we'll be looking into, you can just use a model like that to do the feature extraction, even though you're working on different classes, and it works pretty well. So for computer vision, for object detection, I say it's always worth considering, unless you have the full data set or you intend to just retrain it end to end yourself.
Yeah, and we will. This is a real problem in segmentation. It's a real big problem, and we'll talk about when we get to segmentation that there's just not enough data out there, segmentation training data sets out there. So how do we really tackle this problem going forward? And we'll talk about that. So I don't want to. I think this is, once again, David's code really gets into a lot of these concepts. So I think this is a good point to hand off, I believe. And do you just want to go to your notebook?
Yes, please. So we have about 20 minutes before the break, I think. So let's just, if you can pull up the notebook, and then I think I can take the
do you want me to drive?
For the first one, I think we can try that. I don't
Okay.
know. And if I don't like what you're doing, I just take over.
So
there are 2 notebooks, and both of them are in the GitHub repository. The first notebook is really just like slides, basically. There's not really any code. It's just to talk you through some of the basics. I still like doing that in a notebook. with Markdown available. And if you check them out later, if you want to do some notes yourself, that's always also something that works very nicely in a notebook. So this will focus on the basics of object detection, and we do that before the break. And really just the basics, given that we have 20 minutes available. What we will be doing after the break is a hands-on example, picking one of the models and looking into how would I actually implement that using PyTorch. And so what is object detection? We've been looking into that on a different slide as well. I don't know if I need the pointer, but can give it a try. Figure out how that works.
Tera.
So yes, Mo has been covering that. So it starts with computer vision starts with an image classification problem. That's really the easiest use case of a computer vision problem, where you have an entire image, and you just need to decide: is this a hot dog, or is this not a hot dog, or is this a cat, or is this not a cat? And the next step would then be a localization problem. You have an image, you know potentially that there's a hot dog, and you have to find where in the image is my hot dog or is my cat. And what we're looking into for object detection is actually a combination of those two problems, the localization problem and the classification problem. So the first step usually is identifying objects that I'm interested in with, identify the location, and this is usually done in the object detection case using a bounding box. So this rectangle describing x, y, and the width and the height of where the bounding box or where that object is, and then also doing a classification of that bounding box, where I decide what is it actually I'm seeing. Is it a cat? Is it a dog? Or is it a hot dog? Or is it whatever? Right? And so what we if you can walk down just a little bit on, I don't know if that's what we go through in this session. Just a very brief overview of what are data sets we work with, and I just picked two common data sets. What metrics do we use to evaluate our models, the models we're building, and the final one? And I will have to rush through it, but what is the state of the art in object detection? What kind of models are really the state of the art at the moment? So for data sets, they're basically, there are data sets for specific purposes. For example, I mentioned Kitty, which is annotated traffic scenes. So if you look into autonomous driving, these kind of applications, it comes with data sets annotated with traffic scenes, both segmentation and boxes. But really, if you look into general purpose, there are two main data sets that are basically used. The first one is the Pascal visual object classes data set. In its latest version from 2012, I believe, with about 11,000 images and 27,000 annotated objects for 20 classes. So 20 classes I want to predict. And the images are, and that's often the case, by the way, as well, obtained from Flickr. So what happens is, what people constructing these data sets often are doing is they look for Flickr for images with the right licenses, put them to like Amazon MTurk, and have people annotate the bounding boxes, and that's how those, or researchers if they have the time doing it. There are some links, and this is the data set we'll be using later for the hands-on example. And so the annotation, just another example, is for that specific purpose, comes with XML-based annotations, which then you need to pass, and in order to be able to work with it, we look into that in a bit. And so what you see here, it basically points out I have an image. There's the name of that image on top. What's the size of that image? So the images do not all have the same size, so you may want to resize them before you input them into your model, something we'll be doing. And then also, what objects do I find? So this is an object I find here. It's actually it's of class 21, so it's an extended annotation. And then where's the bounding box? X min, X max, and Y min, Y max. And so the labels you get in the standard VOC data set, which we will be working with later, are those 20 labels here. So very all-day objects like aeroplane, bicycle, bird, boat, bottle, bus, car, and so on. I don't know how they came up with these specific objects, but that's fine. And so this is just an example from the paper describing the data set where you see some of the objects and some of the annotations in those objects. And the other data set, which is really popular at the moment, it's a bit more modern from starting 2015, but there's still ongoing competitions, is the COCO data set. So it's Common Objects in Context, and I believe Microsoft has been releasing this data set, and you get a lot more images with that COCO data set, so a lot more training data. You get more classes with these data sets. You have, for example, for the object categories, you have 80 different categories. Those are the categories mentioned here. So you have a little bit more. You have things like sandwich, frisbee, tie. So a little bit more to detect. You also have other types of annotations. So it doesn't only come with the bounding boxes. It also comes with, for example, segmentation annotations, different types of annotations for different use cases.
Question. I should know this. Both of these data sets are pre-built into PyTorch.
So the VOC, I don't think so.
Okay.
There's what I mentioned here. There's a dataset reader for Torch for Cocoa. Yeah. So Cocoa has a data reader pre-built.
Oh, just a reader, but you have to provide your own data.
You have to download it.
Okay.
This is quite large, the dataset, right? Yes. And even the VOC dataset in the one I was using for that demo is about 2 gigabytes. So it's
okay.
It's something you have to download yourself.
Yep.
Yeah. And we can skip this list. I just wanted to have some code in here. And so for metrics, how do I go about evaluating my models I'm creating, or what do these competitions do? So those are competitions, VOC and Cocoa, and evaluating the performance of object detection. So basically, what metrics need to do are evaluating 2 things: how good am I at classifying my objects, but also how good am I at localization of my objects. So the classification is usually a classification problem. The localization is usually a regression problem, even though that's not true for one of the networks or some of the networks we'll be looking at. And so the way this works, and I start with some basics. So precision recall, just to have a refresh in case you need that. This is something I always like to show from the Wikipedia page. Precision is my false positive rate, meaning that amongst those objects I've actually detected how many are correctly detected. Recall is a little bit the opposite. So how many of the objects I was supposed to detect have I actually detected? So those are the 2 metrics. And so from there, precision and recall, I get to something called average precision, which well, there's a precision recall curve, which is the PR I mentioned here, which just generates precision and recall at varying confidence thresholds. So you get recall on the y-axis, you get precision on the x-axis, and then what AP does, the average precision does, is calculate the average value of that curve. So what is my precision and recall, and what's the average across all different confidence thresholds? And then the next one, very important for regression, or how good am I at detecting bounding boxes, and on what will be what most projects are using, what also we'll be using later, is intersection over union. So I have a ground truth bounding box, so I know that's correct, and I have a predicted bounding box. What's actually the intersect of those bounding boxes, and what's the union? So the dividing the overlap of 2 bounding boxes with the union of 2 bounding boxes is this what we call intersection over union. And then coming to the final metric, which is usually what what Cocoa is using, or what Pascal VOC is using, is mean average precision. So it combines all of the things we've been looking at. I want to know what's my average precision over all classes and over all intersection over unions, and again at different confidence thresholds, or using a minimum IOU. And so for Pascal VOC, for example, for at least the 2007 competition, it was evaluated how well models perform at mean average precision over those 20 classes at an intersection over union of at least 0.5. So that's the minimum intersection I need to achieve in order to be included in this evaluation for this object detection. And what Cocoa is using in its latest or last year version is it actually looks at different confidence thresholds. So different confidence thresholds for those IOUs. Okay, and final section. I don't know if time we've left.
Yeah. 10 minutes.
Okay, so now we get to the point where we look at what are object detectors that are actually out there. So what's the state of the art in object detection? And there are two, on a very high level, there are two different types of networks for object detection. The first one is a one-shot detector network, which does both the localization and the classification problem in one stage. And the other one is a two-shot detector network, which came earlier, which do object detection classification problem in two different processes at two stages. And so the difference usually is that the second one, the two-shot, at least historically, were more precise, but they also take a lot longer to process. So if you need real-time inference models, you would have to look at one-shot detector networks. If real-time is not a big deal, you may have to look at two-shot detector networks because they give the higher accuracy. And so the first two-shot detector network that came out was RCNN in 2014, which basically did use a convolutional network to run or extract different region proposals on the network, and then used a proposal algorithm called selective search, reducing those. So it came up with about 2,000 region proposals, running a convolutional network over this entire image, came up with then a selective search, reducing those proposals to a sum I can actually deal with, then using the CNN, extracting some of the features for those region proposals. So obviously running a CNN on 2,000 different subparts of an image is a long process, and it took quite a long while. So the smartness here was using the selective search and have maybe only 10 or 20 region proposals I need to be looking at. So that's what the RCNN was doing. And then in the final step, there was an SVM that was used to predict. So the region proposals come up with looking into what kind of objects do I find and where. And then there was an SVM in the end run on top of that output to predict what is actually my bounding box. So that's why it's a two-stage problem. And so the next one, I just have to rush through it. Just so some of the points I highlighted in bold are really the points that were added from my perspective. Next, also in 2014, was SPPNet. So one of the main changes here was changing from a max pooling layer to a spatial pooling layer, which then allowed different types of image sizes be processed into a constant number of bins, which again led to speeding up the RCNN. But then quickly, also in 2015, came already fast RCNN, which was again more popular. And one of the things it did is actually no longer do the regression back bounding detection as an SVM, but include it in the neural network. So that was now the big change in fast RCNN. I don't have to do a follow-up SVM for the bounding box protection. I move it into that neural network and have two different heads of the network doing both in one network. And in 2016, something came out that was called faster RCNN. I don't know, they were not really creative with names, I think. So what that did is it took that selective search, which RCNN introduced, and replaced it with a different type of identifying what are actually the regions of the image I wanted to look at. So it used a small CNN. Selective search was more a heuristic based on some traditional computer vision approaches. And it used the idea of anchor boxes. I have it a bit more down. So anchor boxes are fixed ratio or fixed sized boxes I move across the image, which represent shapes that often enough really appear in the image, and and then only predict for these anchor boxes, and is this something I'm interested in or not? And so one-stage object detectors is the next thing, and the main one I wanted to focus on here is YOLO, because that's also what we will be implementing after. YOLO stands for You Only Look Once, so it does. Yeah, I know. It does everything in one approach. It's actually super fast. So YOLO version 1 came out, was maybe not as accurate as some of the other existing models, but it was super fast. 2015, and there were lots of iterations. Last version coming out in 2018. And if you go down a bit. I don't have to go through all of the details. What it does, or maybe the top one. So that's the YOLO V1 architecture. That's what we're going to implement after the break. It basically takes a convolutional network for the feature extraction, and in the end, it has a linear layer to do both the classification and the bounding box prediction in one shot. What YOLO does is it divides the image it sees into grids, and S is the number of boxes I have on each of the axes. So for the problem we'll be looking at a 7 × 7 grid over the image, and each of the box in the grid is responsible to predict maximum of one object, right? So for each of the boxes, you get two things. You get a classification, or you get a prediction of a bounding box, which usually that would be around that box being in the middle of that bounding box. And for each of the bounding boxes, or each of the grids, you also get a classification for what type of object is that. So, for example, a dog, right? And if you go further down, okay, that's not covered here. I'll go into this in a little bit detail after the break, where we look into implementing YOLO. So that's the exercise I wanted to go through. There are other approaches for one-shot detection. I will not really go into that in a lot of detail now. One thing I want to mention, though, is state of the art for that one-shot detection at the moment is either YOLO version 3, or it's going to be RetinaNet, which is another contribution. And again, some of the changes are marginal in each of the editions that are coming. For example, RetinaNet has a different loss function, and if I use a different loss function, my model training behaves differently. And that was a loss function that, for example, led to a significantly increase in accuracy. And mask RCNN is an interesting one. It's not entirely covered, but mask RCNN is...
I'll cover it.
You cover it. Yeah. So that's why it's not entirely covered here. It's something that does both segmentation and object detection in a single network. So if you look into the state of the art, just some screenshots. I think most of them come actually from the YOLO authors, so it may be a bit biased. Yeah. This is, you see YOLO v3. This is all on the COCO train data set, and the MAP we were discussing, what is it the model actually achieved. And you see, for example, YOLO v3. This is a different convolutional architectures, I believe. They were run on is in the range of 50s, and you have other models that are all in a similar range. If you go to some of the older models like YOLO v2 or Tiny YOLO, which is a small version of the network, you get to 20 or get to 48. So there has been an improvement, or lots of improvement made over the last years in 2018. If you go to the next one, this is just another comparison. Now, maybe the final one also interesting. Puts maybe a different spin on it. I like to cover this one. So this one shows that RetinaNet, for example, has the highest average precision for some of the data sets. I believe this is also on the COCO data set. So taking different sources, you see RetinaNet is actually doing pretty well. This perspective, the last one I put here because it also highlights the time. So what are the frames per second I can achieve with each of the different models is an interesting aspect. So YOLO 1, I don't know what the second here means, but it has about 50 frames per second you can achieve on state-of-the-art hardware. And you see how that compares to RCNN, which we were discussing earlier in a bit. RCNN is 47 seconds. So this is something you cannot really use in real time. Mask RCNN with 2.5 seconds. RetinaNet is in the beginning with, or 2.5 frames per second. So RetinaNet is in the beginning with, here it's with 5 frames per second. And if the overall status at the moment, if just the last line, which is not really seen here, in 2017 was, from my perspective, basically faster. RCNN had potentially the best accuracy numbers. SSD, which I rushed through a little bit because there's not much difference for me to YOLO. It's had good trade-off between speed and precision, and YOLO was really the fastest network. Now, if you go to 2018, I think, and looking at these numbers, I think there's a confirmation here. RetinaNet has the highest accuracy for most of the use cases, although it's pretty comparable to YOLO version 3, and YOLO version 3 is the fastest amongst those with the highest accuracy. I mean, you can always be fast, but then you end up with no prediction. But if you want speed in real time, I think YOLO V3 is the way to go.
Just a few comments on thank you for just a few things that I came across when David was presenting. From things I mentioned earlier, look at this, right? Remember how I was saying that everybody doesn't just start from scratch, and you can see the backbone of some of these models is ResNet, Inception. These are some really popular models that have performed well on image classification tasks for ImageNet, and so they've taken that as the starting point from pre-trained, right? So because you don't want to start training from scratch. That's one of them. And then the other thing I was going to mention is that if you are really interested in this field, and if you want to keep track of all these things and how do we find out about these things, is that to me there are three major conferences where people who are working on all this stuff, they wait to that point where they present their results, right? So CVPR, which is computer vision and pattern recognition, which happens over the summer. ICCV, which is International Conference on Computer Vision. I think that's what it stands for. I think that happens earlier in the winter time. And then ECCV, which is European Computer Vision Conference, which is happening next week. So those are the three major conferences. So if you look at like some of the reviews or some of the articles from those conferences, you will see they have also, so for example, David mentioned, COCO dataset, right? They have, it will say on their page, right? There's some of what's going on right now. So there is, what are some of the tasks like? So there is a detection challenge right now that will be presented at ECCV 2018, which is going to be next week. So there's a workshop, and so we'll find out what's going to be the newest and the latest in object detection for COCO after next week, when the teams who have submitted their work, they're going to be presenting next. Oh, sorry if this is too tiny. So this is one way to keep track of all the happenings and what are the latest models, and typically people will publish their models, and maybe a lot of them will be in PyTorch, and so you can just say, oh, okay, I can just start looking at it. Or if it's in TensorFlow, then somebody is going to say, oh, I'm going to implement this in PyTorch, right? So there's a lot of, you can just, so once you find out something like, RetinaNet, right? Just Google, and maybe you can find the PyTorch version of it, right? So just something to keep in mind. And I think we are just about at the break, but I couldn't help but show you guys. This is it. A demo of YOLO V3. So as you can see in real time, it does pretty well,
I wish she'd get a seat, but she only cares when she's got the time. And I fret so much about her loving. I wish she'd let.
These are some of his personal videos, like for a person who
But I'm too cool to admit it when the friends talk to my girl. I ain't
horse. It's saying horse, right?
but I'm too cool to admit it when the friends talk to my girl.
So there's misclassification, right? It got the bounding box correct, but the label is misclassification. Anyway, it's break time.
Talk to my girl.
We'll see everybody back at top of the hour, 11 o'clock.